Hello and welcome back. In the last episode, we added our positional correction that our bodies are not going to slide into each other anymore. In this episode, we are going to create everything necessary for our rotational impulses, and this is calculating inertia. Inertia is used, is needed to calculate anything with rotation. It's like if you start trying to move something in a specific direction, then there's kind of a resistance, when you try to rotate something. And this resistance, the reason of this resistance is the inertia. And yeah, we are going to implement the calculation for inertia for rectangles, for simple rectangles, for circles, and for polygons, for any convex polygons. We do the first things first, the rectangle. Going to implement it for the rectangle and for the circle first, and then we're going to the polygon. Okay, then let's jump to the circle first. For the circle, that's a really, really simple formula. And we can do that. Of course, you can also do this by or in the rigid body, and then you check which shape you have. I'm gonna do it in the shape class. And yeah, I'm gonna call this calculate inertia. And for circles, it's gonna be half. Well, it's gonna be the mass. Yeah, of course I'm gonna pass the mass as a parameter, and then I'm gonna say mass times the radius of the circle. It's a squared, so times mass times radius, and then half of it, and that's the inertia for circles. We call this in the rigid body at the really top, like we did for the mass. I think I'm gonna do it like right below everything else. So I'm gonna call here this dot inertia is this dot shape dot calculate inertia with this dot mass. Okay, and then I'm gonna say if this dot inertia is greater than let's say a small amount, then this dot invert inertia. We're also going to use the invert inertia. Then we can calculate this one. And if it's smaller, then this small error, this is called a bias. It's because of floating point errors. Yeah, and if it's smaller than this one, I'm gonna say it's 0. And the same thing with this one, I'm gonna do the same thing to the mass. There we go. Yeah, we can also log the inertia. So I'm gonna say console.log inertia, this dot inertia. There we go. Okay. What I'm also gonna add is a angular velocity. We need this one too. Gonna add this right below the velocity. Gonna say angular velocity 0. Or, I mean, I can also say rotational velocity because angular might be a bit irritating. But I just leave it like this now. All right. And then I'm gonna add, yeah, I'm just gonna add a get angular velocity to, there you go, get angular velocity, this dot angular velocity return. All right, and that's everything we need to, well, almost. I'm gonna add here, like we did for the velocity, it's the exact same thing as for the velocity, but here I'm gonna scale it also by 0.999, and I'm gonna change this one also by to 999. And I think that's it now. We of course need to integrate the angular velocity. I think, yeah, I'm gonna do this run also. So let delta rotation is equal to this dot angular velocity times delta time. Then we get a delta rotation, and then we can say this dot shape dot rotate with the delta rotation. Okay. We're gonna do the same thing for the other integration methods too, but later on. Not in this episode. We're gonna do that when we are grabbing the objects. Then we're gonna add this one to the other ones too. All right? Good. Then we can go back to the calculation of the inertia. Let's go first to the rectangle. And here, how did I do this here? Okay, yeah. I'm just gonna copy the calculate inertia method from the circle, add it to the rectangle too. And the calculation for a rectangle is a little bit more complex. We still say mass times, and then it's the width times the width plus the height plus the height. And this we're going to divide by 12. And that's the inertia for a rectangle. And now to the polygon. The polygon is more complex. The polygon, where do I have the polygon? There we go. Yeah, I'm just gonna add the method again. There we go. What we're gonna do for the polygon now is we are getting the mass for a triangle first. So we triangulate basically the polygon. Since it's a convex polygon, we can just use the centroid, and we're gonna triangulate this polygon around the centroid, okay? And then we get the mass per triangle face. We can calculate this one, mass per triangle face. We're just gonna divide the mass by the vertices length. And then we are using this mass per triangle face. Yeah, I think by calculating the area of a triangle. Yeah, and that's might be a little difficult to understand what we're doing next. I think it's better to just code it and try to understand while we're coding it. There are also some articles out there. Yeah, it's like the same we did with the calculating centroid. Yeah, just code it along, and then you have it. You can use it for every convex polygon then. All right, then let inertia is equal to 0. That's our result inertia. We can already return it. Cool. And then I'm going to calculate the mass per triangle face. Is the mass divided by this dot vertices dot length. Then we need to iterate through every, not focus, through every vertice. So let I is equal to 0. I smaller than this dot vertices length, then I plus plus, and then I'm gonna say let. Then we're gonna do a direction vector from the center to the first vertice. This will be center to vertice, let's say 0, is the subtraction from this dot centroid. Oh, sorry, from this dot vertices. There we go. We subtract yeah, centroid from vertice. Is that right? The right direction? Right order, I guess. Yeah, then we have a direction vector to the vertice. Then I'm gonna call the index method, the math helper index method, but I'm gonna store the index. So the index vertice 1 is equal to math helper index, and this is I plus 1, and list dot vertices length. Okay. I think I can say here also, you can also say center to vertice or the two current vertice, and this is the index for the next vertice, like we did in the collision detection step, I guess. Yeah, but I'm gonna do it like this now. Then we do a direction vector to the next vertice, so center to vertice 1 is the subtraction again. This dot vertices at the index vertice 1 to the centroid. All right. And then we get the triangle, the inertia for a triangle. And we can call this by saying inertia triangle is equal to mass per triangle face, all right? And then we are multiplying this one. Now we're calculating the area of a triangle. I'm gonna say length 2, plus center vertice 1 dot length 2, and then plus center to vertice 0 with the dot product to center vertice 1. All right, and at the last step we have to divide it by 6, and then we have the inertia for one single triangle. All right. I made a mistake here. I said that this is the area of a triangle. That's not true. Actually, this whole line here is a formula to calculate the inertia for a triangle, for one triangle. Okay, so I made a little mistake there. But now we have the inertia for a triangle. The good thing is now we are almost done. We just have to sum up the inertia now. So just call inertia plus equals inertia triangle, and then we have it. And then we can return our inertia, and that's it. All right. I think that's already everything. We can print our inertia then. I think I already did this somewhere in the rigid body class, I think. Yeah, right there. Yeah, let's see. What's our inertia, right? Then jump to the web browser. I'm gonna open the console somewhere when I find it. There we go. And let's refresh and see how much. Oh, okay. Yeah, that's a problem. I'm gonna remove the code which prints the nulls. That's right here. Okay, let's jump back and refresh. And there's still, okay, yeah, we have a collision and somewhere the collision things is printed out, and that's in the collision manifold. I'm gonna remove this one too. This is this one. And collision detection 78 and 14. 78, where is it? There we go. I'm gonna remove this one too. Okay, save. Go back to the browser, refresh, and there we go. That's our inertia. We have, oh wow, we have an inertia of 250,000, 83,000, 83,000, and 180,000. We can actually test if the inertia is right. We have two rectangles which are basically the same. I'm gonna change the weight of this one too to 20. This one has the exact same, well, both of these, all the three have the exact same, or must be the exact same inertia, and we can call one time this method here, and we can compare these two inertia approaches. All right, let's do this. I'm gonna just take this whole code here and put it into the rectangle method. So let's just paste it in here. I think that should still work. I'm gonna say console.log inertia formula is equal to, well, it's plus inertia, and then this one. Let's do it like this, and I'm gonna console log this one too. This will be inertia 2. We're gonna return just inertia. Yeah, I'm gonna redo that anyways. Formula, let's say 2. All right. Then hopefully I did everything right. All right, I did. Yeah, and you can see here at first there is no inertia, but later that's the exact same inertia we want. Inertia formula and inertia formula 2. This one is the inertia for the circle. And yeah, our formula is working exactly right, exactly the same. This one, of course, needs a bit more performance, but since we're doing this only once, then it's actually doesn't matter. You can also use this method for a rectangle, the formula one. You can also use this one here for rectangles too. All right. Yeah, I'm gonna redo everything. And that's it for calculating inertia. In the next episode, we finally see our physics engine. Yeah, we basically finish our most basic physics engine now by adding a rotational impulse. Then we see our objects rotating and behaving correctly. All right. Yeah, that's it for this one. Thank you for watching and see you in the next one. Bye bye.